Every star's story begins in a vast, cold cloud of gas and dust known as a nebula. These stellar nurseries are the raw material of the cosmos. Gravity, the fundamental force of attraction, starts to pull clumps of this material together. As gravity draws more and more matter into a central point, the clump begins to spin and heat up. This collapsing, rotating cloud is called a protostar. It's not yet a true star, but it's on its way. The protostar continues to gather mass and contract. Its core becomes incredibly dense and hot. This process can take millions of years, depending on the star's eventual size. When the core of the protostar reaches a critical temperature and pressure, nuclear fusion ignites. Hydrogen atoms fuse together to form helium, releasing enormous amounts of energy. This marks the birth of a true star. The star enters the longest phase of its life, known as the main sequence. During this time, the outward pressure from fusion perfectly balances the inward pull of gravity. This equilibrium keeps the star stable. Our own Sun is currently a main sequence star, about halfway through this phase. The duration of the main sequence depends heavily on the star's mass. More massive stars burn through their fuel much faster. Eventually, the star exhausts the hydrogen fuel in its core. Without the outward pressure from hydrogen fusion, gravity begins to win, causing the core to contract and heat up further. This contraction heats the outer layers, causing them to expand dramatically. For stars like our Sun, this expansion turns them into a red giant. For much more massive stars, they become red supergiants. The star's surface cools as it expands, giving it a reddish hue. In the core of a red giant or supergiant, if it's massive enough, helium fusion can begin, creating heavier elements like carbon and oxygen. More massive stars can fuse even heavier elements in their cores. The ultimate fate of a star depends entirely on its initial mass. Low to medium mass stars, after shedding their outer layers as a planetary nebula, leave behind a hot, dense core. This core is called a white dwarf. A white dwarf is essentially the leftover ash of a star's core, slowly cooling over billions of years. It no longer undergoes fusion, but is supported by electron degeneracy pressure, preventing further collapse. Much more massive stars face a different, far more dramatic end. Once fusion in their core stops, gravity causes an incredibly rapid collapse. For massive stars, the core collapse triggers a catastrophic explosion known as a supernova. This is one of the most powerful events in the universe, briefly outshining entire galaxies. The explosion blasts the star's outer layers and newly fused heavy elements into space. What remains after a supernova depends on the star's initial mass. If the core is between about 1.4 and 3 times the mass of the Sun, it collapses into an incredibly dense neutron star. A neutron star is composed almost entirely of neutrons. If the core is more massive than about 3 solar masses, gravity overwhelms all other forces. It collapses completely, forming a black hole, a region of spacetime where gravity is so strong nothing, not even light, can escape. The material ejected by supernova enriches the interstellar medium with heavy elements. These elements are the building blocks for new stars, planets, and even life itself, completing the cosmic cycle.